Yeah, so my name is Ittai Abraham. I'm part of the research group at VMware. And I'll be talking about decentralized trusts and why I think this is kind of the core aspect of this new disruption. Here's one of my favorite quotes. This is an email that Satoshi Nakamoto sent, I think, a few weeks after publishing the Bitcoin white paper. And he tries to explain what Bitcoin is in terms of innovation for computer science. And he says, the proof of work chain is a solution to the Byzantine generals problem. And I'll try to rephrase it in that context. And I think one of the interesting things here is really this idea that the main core innovation in Bitcoin was solving Byzantine agreement. And this is how I got introduced to this topic. I've been studying the questions of Byzantine agreement for over 15 years. And indeed, this was kind of one of the big disruptions in this area that enabled this new revolution. And we've been starting to think about this and trying to figure out, what are the other components that need to be solved in order to innovate in this area. And what we're seeing is really this is kind of an interdisciplinary effort with several different components. So obviously there is a very deep component related to economics. And one of my favorite definitions of economics is that it's the study of decision making under scarce resources. So again, there's two things that need to happen. One is that you need to be able to make decisions, and the other is that there is scarce resources. And really this is kind of captures a lot of the idea that there is some value that needs to be jointly partition between a group of members, and how this value is being partitioned and how people are incentivized to take their action is kind of key to what economics study. What economics typically does not look at as much is it does not look at collusion, it does not look at what happens if you have malicious attackers. And really this is kind of one of the amazing reasons why we want to use also cryptography. So cryptography is this core part of theoretical computer science. And one of the ways I like to define what cryptography does is it provides you with protocols that replace trusted parties. So for example, you could think about a zero-knowledge proof, which is a protocol between a prover and a receiver, is actually replacing the fact that we have some trusted party that the prover can send the whole proof to, the trusted party will verify it, and the verifier just gets the information from the trusted party whether that proof works or doesn't work. And you can actually cast all of the cryptographic innovation in this kind of language of replacing ideal functionalities or trusted third parties. And as Vitalik said in the morning, there's been a lot of progress in this area of cryptography, even in the last 3 weeks, but also in the last 5 years. And I think even in the last 20 or 25 years, just amazing changes and the new types of mathematics that enable these things is quite impressive, and I believe it's going to have a profound impact on society. One of the things that cryptography typically does not do is it does not study incentives. It usually assumes kind of this good guy, bad guy mode. And cryptography typically also does not handle things like asynchrony and network delays. It typically kind of assumes a more a standard protocol structure. And this is where the third area comes into mind, which is distributed computing. And distributed computing really tries to figure out how to build these large-scale systems. And how to build them and how to deal with all the problems we have when we have network delays, when we have adversaries who are trying to block us, when we have problems with asynchrony, and so on. And one of the core questions that distributed computing tries to solve is this question of Byzantine agreement. And so what we're seeing here is that the combination of all these three together are providing us kind of with this new and very innovative potential. And what I'm seeing is that the middle of these three intersections is where this disruption is happening. So it's really kind of an interdisciplinary effort. And if you had to ask me 2 years ago, I would say this is kind of the three main themes and topics. But what we've seen in the last year is that this innovation, in some sense, is so foundational to society that it's actually affecting the foundations of how we live. And in that sense, it's not just about these subjects, but the current way that we're thinking about it is it's also about governance. And when I talk about governance here, this is not about questions of on-chain and off-chain governance in the blockchain space, although there's kind of a lot of amazing technology in that area as well. But really, governance is kind of the study of social norms, of laws, and of institutions, and how society manages itself. And what we have to realize is that this new area of cryptocurrency, you can have the best type of cryptographic protocols and the best type of distributed computing ideas and the most efficient incentive solutions. You have to understand that you're not living in a void, right? We're living in a society, and we have to adjust the innovation to the social norms that we currently have, and we have to also innovate in that area of governance. So how will these social norms and what will the institutions in the 21st century look like? And in that sense, I think this combination of these three in addition to governance, is what will provide us with solutions in the future. Right, so today I'm going to talk to you about two topics, and this is kind of about decentralized trust. So I'm going to try to tell you what it is and what is this decentralized trust paradigm. And the second thing I'm going to say is talk about this idea of abstraction. I'll show you why we believe it's a very powerful one. So I want to start with a very, very loaded word. This is trust. Right, and I'm going to claim that trust is kind of a foundation of our society and the fact that we have a thriving economy. So in a way, you should think about trust as your guarantee about the future. And if you think about, for example, a lot of the value in the 21st century is going to be focused on providing trusts in this new world. We live in a world which has a lot of uncertainty. And what trust is trying to do is provide us more certainty in this very uncertain world. And if you think about, for example, Ethereum, so part of the value in Ethereum is really the trust we have in Ethereum that it will take this journey of decentralization and provide us with this trust. I would argue that one of the challenges that, for example, Libra has to work through is gaining trust of members to use it and of consumers to use it. And looking less at the future and more at the past, we've seen a lot of cases where we've provided trust to economic entities. So for example, we've given our private data to different entities, and we've trusted them to use it in a correct way and not to abuse it. And what we're seeing now is that people are more interested in finding ways to get stronger guarantees about the trust, for example, of their privacy. Money is another example of something that we provide trust in. So we trust that if we have $100 today, it will be valuable and we can use it tomorrow. For example, if you live in a place that has a lot of inflation, so Venezuela is a good recent example, then that type of trust actually erodes. The value of the Venezuelan currency is actually eroding over time, and this trust about the future is eroding. And so the fact that you get trust from money is a non-trivial fact. In fact, some of the reason that Bitcoin is appreciated is because it has this property that there is some trust that it will not change in terms of the total amount of coins over time. And so one of the ways you can get this trust is by not relying on a specific entity, but actually distributing this or decentralizing this over a larger set of groups. And this is kind of the main theme and the main innovation in these cryptocurrencies, where instead of trusting one entity, one bank, or one central bank, there's kind of a decentralization of this effort. So in particular, the idea here is that you don't want to depend on a single server. And what you'd like an infrastructure that will provide you this trust, and I'll try to say exactly what it means. So I'll focus on three different things. The first thing is safety. The second thing is liveness. And the third is privacy. And what you like to do is you like to maintain these three types of properties, even if you have an adversary or an attacker that compromises or colludes to compromise part of your system. So really the goal is to try to get these three types of properties. And this is what I claim is the foundation of decentralized trust. So going into a little bit more detail, the idea here is that compromise means that there's an attacker that controls part of your system. And even though the attacker controls part of your system as a whole continues to behave in a trusted manner. And the liveness property really means that the system continues to work no matter what. So we've seen different cases where there's denial of service attacks on systems, where an adversary can basically cause a system to stop reporting actions or stop making transactions. And really what liveness guarantees us is that good things will happen and will happen in a timely manner. The second property that is really important here is safety. Right? And safety is kind of, in the Bitcoin language, this is avoid the double spend attack. This is kind of the core property that you want to obtain, which is that a system will not be able to commit on two different things simultaneously. And this is really kind of the core thing that a Byzantine agreement tries to obtain. And finally, we'd also like a solution that gives you privacy. And privacy in this sense does not kind of mean that you have the minimal, you don't have, nobody knows anything about what you're doing, but in fact there is some sort of social contract which defines what information you are and are not willing to share. And given this social contract, this tells you, what you are happy with and what you are willing to agree on. And what the system guarantees is that whatever this contract is, that degree of privacy will be maintained. So for example, in the future, people cannot abuse your information and get a different notion of privacy. And so these three things together kind of define in what we see as decentralized trust. And there's kind of a common infrastructure for building these things. And so this is kind of a layered architecture that has three different layers. And the top layer is just these applications. And these applications basically are the ones that need a decentralized trust infrastructure to run on top of. And the middle layer is a layer that actually allows you to run applications on it. And for example, this is where you have these smart contract engines. This is where you can add privacy systems on top of it. And so this is kind of the enabler that allows you to run distributed applications. And the bottom layer, and so this is kind of where you can imagine a world where there's multiple different types of execution engines, and I'll go to that kind of in the later stage. And the bottom layer is really this layer that gives you this solid foundation where you have a trust infrastructure that you can build on top of that. So this is the infrastructure that gives you the safety and liveness properties, and on top of that you can build a smart contract engine, and on top of that you can build distributed applications. And when we look at the different projects that we're seeing, both in the permission space and the permissionless space, in the cryptocurrency world, you can map all of them into these three layers. So this is kind of a general framework for how decentralized trust architectures look like. And indeed, this is kind of the vision that we have about how these systems should look like, should evolve. And yeah, and this bottom layer, it can deal with the infrastructure challenges, things like reconfiguration, cross-chain transactions, and sharding. This can all be dealt in the lower level, so that these higher levels benefit from these types of abstractions. And so what I want to focus now is on this paradigm of how you would build this lower level. And what this lower level does is it actually gives you a fault-tolerant replication of a state machine. So a state machine is just a generic way to define a generic type of computation. And what you would like to have is you'd like to replicate this using a Byzantine fault-tolerant system. And so in particular, this is kind of the Byzantine fault-tolerant state machine replication paradigm. And it's based, this is not a new idea. This is based on over 30 years of academic research. And I'm pointing here mainly on PBFT. This is this beautiful work done by Barbara Liskov's group at MIT, but there's been a lot of others even before that. And this basic idea is to have this primary backup paradigm where in every view there is one leader that is transmitting transactions, and the remaining are replicas that are replicating the action of this primary. And you can have a rotating primary and so on, but this is kind of the main high-level idea. And the core here is to have a view change mechanism that it will allow you to deal with a primary that's faulty. So this is kind of the technique that allows you to change from one primary to the other. So these systems are always safe. They maintain safety and no double spend, even if the system partitions, even if there's a full denial of service attack. And they maintain the liveness when the system stabilizes. So if there's kind of a full denial of service attack, then you can't make progress. But once the system stabilizes, then you get liveness and you can make progress. In particular, these types of systems allow you to get these properties under this notion that the size of the attacker is less than 1/3 of the whole population of the replicas. And this is kind of the optimal bound for these types of systems. And so this is kind of our view of how these things should be built. But if you think about it and you look at what both people are doing in the permissionless space, so Casper and Tendermint and many proof-of-stake protocols, and also what's happening in the permission space, this is exactly the same type of paradigm. So I'm going to tell you a little bit about our work here. This is SBFT. It's a decentralized trust infrastructure. This is a scalable Byzantine fault-tolerant system. It's a collaboration between VMware and academic partners. It's been recently published at DSN this year. And it kind of uses new algorithmic ideas to get the same type of state machine replication, but at scale. So to work with a larger group of replicas and to get high performance. In particular, we use these techniques of collectors to avoid quadratic messages. We use BLS signatures to reduce proof length and to get better efficiency. And it has this kind of very nice ability to have a fast optimistic path. This is a Byzantine agreement with a fast optimistic path, which is actually unique because previous systems have tried to do that and failed. And so this protocol at least has a guaranteed correctness safety. And so we have experiments, and this is kind of one of the main advantages, is that we're, I guess, the only system that has been submitted, to academic, rigorous research and published their benchmarks, where we actually deployed the system on 200 nodes and managed to get good performance relative to competitors. So really our focus was on getting high performance on a highly scalable type of deployment. And finally, since this kind of project transitioned from being a research project to being a product, and so at VMware we're really developing kind of an enterprise-grade version of SBFT, and this is Project Concord. So Project Concord takes all the nice ideas of the academic ideas of SBFT and builds kind of an enterprise-grade version of that. Here's the recent announcement, I think this is 3 weeks ago, about a joint partnership between ASX, Digital Asset, and VMware. And this is an example of some of the places where using our technology, SBFT, and this state machine replication approach is gaining momentum. And so what I want to say here is really about this connection between the permissionless world and the permission world. In particular, this kind of realization in the cryptocurrency world that proof of work is probably not a viable path forward. There's been a lot of discussion about the amount of energy that it takes and the inefficiency in terms of the number of transactions per second and so on. And there's at least a growing consensus among some of the people that this is kind of not the viable path forward. And really we see a joint shared vision where proof of stake and Byzantine fault tolerance is kind of the holy grail that we're all trying to get to. And at least in our view, we're seeing different parts of the this ecosystem trying to get there from different directions. So you're seeing, for example, Ethereum 2.0 is basically starting from a proof of work system and trying to migrate from that towards a proof of stake system and toward a system that provides you with Byzantine fault tolerance. And we've been listening to this process, and we've been gaining a lot from the insights that this process has been doing. And in parallel to that, we've been trying to do similar types of aspects where we start from the permission space. This is a space where basically the participants themselves are predefined. So there's, say, a fixed group of 100 members or a fixed group of 200 members, and this is kind of the permission space, and see how that type of technology can evolve towards this joint vision of proof of stake and Byzantine fault tolerance. And what I'd like to say is that it's not as if these are two different cars that are running in two different directions towards this central goal. There's actually a lot of joint ideas and a lot of good interaction between these two communities. And so we're seeing kind of this, academic lineage where ideas from one area are helping and affecting the thoughts of the other area, and so forth. And so, really, we're seeing here a lot of different types of work. So here's, for example, PBFT, which was very influential for our work in SBFT, which evolved to this product offering, which is Concord. A different, very influential paper is this paper by Dwork, Lynch, and Stockmeyer, and that influenced Tendermint. So Tendermint was initially kind of a master thesis and a breakthrough in Byzantine agreement. And this led to the evolution of Tendermint and Cosmos as we know it today. And it really takes ideas from the academic world. And similarly, we're seeing Casper taking ideas from these previous works and also suggesting new innovations and new improvements in Byzantine fault tolerance. And indeed, when we read both Tendermint and Casper, those ideas that came from the permissionless space actually allowed us to make improvements also in the foundation of the Byzantine agreement. This led to this work on hot stuff. And we're seeing more projects, for example, Libra, using ideas of hot stuff and Concord and Casper. And I think Ethereum 2.0 is another example where the goal is to use these types of systems and protocols. And I guess what I want to stress here is really this kind of joint work and joint ecosystem that is kind of moving this world forward. All right, so I'm switching to the last topic, which is about the power of abstraction and generic execution. And again, I'm going back to Barbara Liskov. She's a Turing Award winner, and the title of her Turing Award talk was The Power of Abstraction. And really this idea that you can separate concerns and think about abstract things, there's a lot of advantage in building real systems. Right? And we often say, well, a real system, you shouldn't be too abstract, you should have something concrete. But really Barbara was saying, no, you should understand what is the right interface for these systems and build it in a modular way. This is definitely been observed in PBFT, where it's built in a modular way and allows you to do a generic state machine replication. This is kind of one of the beautiful things about it, is that you can define whatever state you want. And we've seen a similar thing in Ethereum. So in our view, one of the core innovations that Ethereum brought to the world is this idea that the state machine that you're replicating is by itself a virtual machine, a Turing complete, interface that allows you to write on top of that arbitrary smart contracts. So really this idea that you can build a generic state machine, and on top of the generic state machine you can build a virtual machine, the EVM, and on top of that you can build contracts, allows you to have all this flexibility. And this is kind of one of the core advantages of Ethereum. And so I think Ethereum 2.0 wants to take the same type of path, where there's be multiple different types of execution engines that could run in different shards, and potentially some of them will run on execution engines based on WebAssembly. So our vision is very similar to that, in the sense that the infrastructure that we've built supports multiple different types of execution environments. So for example, we're supporting today DAML, which is digital assets domain-specific language for the financial industry. We support EVM, which is Ethereum's virtual machine. And there's also some preliminary support for IBM's chain code. But generally, the architecture is such that you can build a generic state machine. And if you like, for example, the Move language or the Move virtual machine, you could easily implement that and run it on different types of state machine replication protocols. And yeah, so soon we will be open sourcing the EVM version that runs on Concord. So part of this project is open source. The Byzantine fault tolerant library is currently open source, and we're hoping that by the end of the month we'll publish, we'll open source also the Ethereum virtual machine, and you can then run contracts, EVM contracts, on a virtual machine that runs on top of Concord. So I'm going to thank you and take any questions.
Hello, can you hear me? Yeah, okay. Can you talk a bit about the differences between the different solutions that VMware offers, hot stuff and SBFT, and if I'm not mistaken, Concur as well?
Sure.
What are they used for from a business perspective?
Sure. So the way you should think about it is these are variants of the same state machine replication approach. I have a blog post trying to explain the differences between, say, SBFT and hot stuff. So one of the differences is this high-level idea of, do you replace leaders every round or do you keep stable leaders? And then there's kind of another difference, which is depending on the specific algorithm for doing view change. But really, you should think about that these are very technical differences. If you zoom out and you're not an expert that's working 15 years in this area, they should all be the same in the sense that they provide you with a Byzantine fault-tolerant state machine, a generic Byzantine fault-tolerant state machine replication system.
Hey, thanks for the talk. You mentioned EVM that can run on Concord. What additional guarantees can you give on like safety and liveness with this like layered approach? Like what can you add to the EVM in that sense?
So in that sense, it'll give you the same type of guarantee that Ethereum 2.0 wanted to give you, which is finality of transactions. So today, when you run the EVM on, say, the Ethereum Byzantine fault-tolerant replication, which is proof of work based, it takes you a while till transactions commit, maybe a few seconds, and maybe you want to wait an hour for finality. What these systems give you is sub-second finality. So in a quarter of a second, you can get a commit certificate. And we believe that that will enable you to do new applications. So the interface will be the same. The applications you write on top of EVM will be exactly the same. It's just that the system will give you much faster and better throughput and much better finality.
Hey, hi, thanks for the talk here. One question. Why did you decide to include proof of stake? Maybe it sounds trivial, but for example, Ripple is using only BFT. It seems to be pretty successful for now. Why include both technologies?
Yeah, so I guess my focus here is on using, or what we believe, similar to Satoshi, I guess, is that the core problem you have to solve is Byzantine fault tolerance. If you're happy with doing it in a permission setting, we are happy with that as well. If you want to use proof of work to decide who gets to be a voter, that's good. And proof of stake is one other way to decide who gets voting rights. But once you get voting rights, in our view, the right protocol or the right approach is for the people that have voting rights to run a Byzantine fault-tolerant state machine replication protocol. Thank you.